December 25th, 2021, NASA launched the most powerful telescope ever made.
If you look at the deepest images from Hubble, what you see there are these little teeny tiny red nuggets. Those reddest galaxies are the edge. But we know that there's something beyond that edge. We need light that is more red than Hubble can see.
Oh, that's so cool. Goosebumps when you think about it's like it drops off, and beyond that, the expanse of what we've never seen. Don't make me laugh too hard today. I always keep a little mirror here just to check if I look okay. I don't need it today. I woke up this morning early to go surfing, and I ended the surf session with a surfboard flying down from the heavens at my eye. I honestly don't feel that bad. I just have a little bit of a headache and 4 stitches and a bruise all over my eyeball, but I'm fine. So, Levi, did you hear that just a little over a month ago, we launched the most powerful space telescope in history? Do you know anything about it?
Not a single thing.
Wow, that's exciting. So, the James Webb Space Telescope is what a lot of people call the successor to Hubble. If this is the size of Earth, it's the size of a quarter, where do you think Hubble is? Like, how far away?
I would think it's so close I wouldn't be able to.
You actually would be able to see it, but it would be about 1 millimeter up. So it'd be really, really small. Where do you think Webb will be?
I would think of right next to Hubble.
No. So Hubble's about 550 kilometers up above the surface of the planet. If Hubble's 1 millimeter, then Webb will be 9 feet away.
Oh my God.
9 feet. So like outside of this room to that chair in the middle of our office.
So far.
Yeah, the things I'm going to tell you about are where it's located, because it's a really unique, special place, what we can see with it that Hubble couldn't see, including why we can see so far back. And I'm going to tell you the crazy engineering that it has to fold up like a little.
Never seen it.
Yeah, it's so cool.
Like a transformer?
Like a transformer. Wait till I show you some of the photos of what we're going to see with infrared. So maybe I'll start there, actually. Have you ever seen this nebula before?
It looks familiar.
I think it's called Mystic Mountain. This is what it looks like in the visible part of the spectrum. And then this is what we see when we look with infrared. You're seeing all this stuff that was obscured, and then you can see straight through it all with infrared. And you can see things that Hubble couldn't see.
Well, a really critical thing about this telescope is that it's an infrared telescope.
All the instruments, all the detectors, basically like all of our camera sensors on Webb are all infrared sensors. So you can see things like this. Here's, a smoky image of a firefighter, but then they can see right through the smoke to see the heat signatures of a hot person there on the floor. Guy holding a trash bag, and you can see straight through the trash bag. Infrared sometimes goes through things that visible light doesn't go through.
And we need that infrared capability to find the very first galaxies, that first epoch of galaxy formation after the Big Bang.
So one of the things scientists want to use Webb for is looking all the way back to the very beginning of the universe. The farther we look away, the further back in time we're looking, because it takes light some time to get to us.
Those galaxies are so far away that their light has been redshifted all the way into the infrared part of the spectrum.
Redshifted always means just downshifted, essentially?
Yeah, longer wavelengths. There it is. We're going that direction.
Light is always essentially moving along that spectrum.
When it's moving through the expanding universe, it is.
So even if we had like a super huge optical telescope in space, much more powerful than Hubble, no matter how big it was, it wouldn't be able to see these galaxies because their light now is all in the infrared.
So looking back in time, here's the Big Bang, which we obviously know from previous videos that it didn't happen at one spot, but with Hubble only saw back to about here. That's right at the end of the first galaxies forming. So Webb is going to be able to see all the way back to here, to the very, very first stars.
Whoa.
Yeah.
That's cool.
It's super cool. Your face lit up. I'm so excited.
That is really cool.
We'll be right back with more space, but a quick word from today's sponsor. If space telescopes are a service to humanity, then this sponsor is a service to the people in the room with you. I've been using native deodorant for a few months now. This one, lavender and rose. But they sent me a few different scents to try out. There's lilac and white tea. This one is coconut and vanilla, which is like a beach party under your arms. And speaking of down under your arms, we've got eucalyptus and mint for all you Aussie lovers. But my personal favorite is the lavender and rose because I love lavender. So this one wins, and it always will. Deodorant. Nearly everyone uses it, and we know if they don't. But Native has choices for deodorant that are more sustainable. They offer this paperboard packaging, which is the same formula as their regular deodorant, but they replace plastic with paper. And they use simple ingredients, so it's very smooth and dries quickly and it's not sticky, plus it is cruelty-free and vegan, which I know is important to some of you. So normally 3 plastic-free deodorants would be $39, but if you use my link and my code PhysicsGirl, all one word, then you'll get them for $26, which is over 33% off. With my code, you also can get 20% off of body wash or toothpaste. And now, if you'll excuse me, I have to get back to editing this video for you. It is a arduous task. So some of these galaxies would actually be invisible to Hubble.
Yes, Hubble is blind to the galaxies. Yeah.
The early stars were 30 to 300 times as massive as the sun, millions of times as bright. They would burn super fast and blow up in supernovas. Some of them would maybe become the first black holes that would eventually become like the supermassive black holes at the center of our galaxies. The oldest light, you know, it's not the oldest because we've actually seen the cosmic microwave background. So
What's so special about getting to see here if we have seen here and know what's here?
we've seen here, but not at a very high resolution. So when you see that map, that cosmic microwave background map, well, it didn't have the smiley face, but this is the light from there. This is the cosmic microwave background. CMB was just from the result of neutral atoms first forming in the universe and light starting to escape. There were no stars yet, but this isn't very good resolution. It's like if you took a picture of every single human on Earth and you're like, let's put everyone together into one circle this big. It would just look like kind of a brownish blob. You wouldn't be able to know that humans have eyes. Stuff that ended up making every single star and galaxy and person and amoeba and everything in our universe all in this little picture.
Yeah, it's a bunch of useless data with no control.
Well, it's not useless. Like, we love the CMB, but in some ways people are like, well, we've seen that far back. But we've never seen this epic.
How come?
Not in enough detail to tell us our basic questions we have about how the very first stars and galaxies ever in the universe formed. This is one of the parts I don't fully know how to explain or fully understand. I mean, besides the obvious that these are the most distant and oldest galaxies in the universe, like that's really cool to see. What exactly is it about how they evolve and what they look like that we're so curious about?
It's sort of just trying to piece together the big picture story of how the universe evolves. So if we look at galaxies in the nearby universe, in general, you know, they're very organized. The Milky Way galaxy has these beautiful spiral arms, but as you start to look in the more distant universe, you see a completely different picture. Galaxies are sort of smaller, they're more clumpy. And so that question of how we go from the sort of small clumpy things to the large organized structure that we see today is one of the central questions of how the universe works. And of course, we look around our Milky Way and we have planets, and on this planet we have people. And so it all, in a sense, you know, connects to that question of how did conscious life evolve? And that has to do somehow with how galaxies evolve.
It's like universe ancient lore. It's like, did you know there were like fewer
They were
stars
just-
and they were way bigger?
Finding these first galaxies was one of the very first sort of drivers for building a telescope like this. So back not long after Hubble was launched, even before that, we were not we, I was like a kid then, but astronomers were thinking about what's the next big telescope? What's the really big thing we want to do? And seeing those distant galaxies has always been sort of part of that story and part of the motivation for why we built the telescope like we did.
We can't just look at our own galaxy to figure out how it formed. We have to look at other galaxies in the past and then extrapolate from that. I don't know what you looked like as a baby, but I can look at you know those like weird apps that take a picture of you and make you look like a baby? The way that those work is that they look at babies and then they extrapolate what are all the baby features, and then they take you and they're like, you must have looked like this. Not quite the same. It's like a baby filter for galaxies. We also want to know where our galaxy's heading, but Andromeda is heading toward the Milky Way for a potential collision. So in the future, it may be an Andromiway.
Yeah.
Oh, so those are the types of things we might get answers to.
Exactly. We continually discover stuff, and then that gives scientists new theories. They're like, oh, we have to test this one now, and then they look for stuff, and that is just going to keep happening with Webb. And then the other thing, the last science we're going to do is we're going to look for life, essentially. How would you look for life?
Yeah, I would look for water.
Yes, beautiful. You look for a specific element. And how do you do that if you're looking at a planet really far away?
By the next best telescope.
You spent $10 billion and sent a telescope called Webb out into space. Telescope costs $10 billion. Yeah. So you'll see a star and it's like luminosity, how bright it is. Will suddenly go bloop, and then it'll come bloop, right back up.
Oh,
and then it'll go bloop. And you're like, what is that? What could that possibly be? And it's a planet, like just barely blocking some of the light and passing in front of the star.
You know, stare at a star, a distant star, and watch for a planet to pass in front of the star. And then they look at the starlight that filters through the atmosphere.
What color is Fanta?
Orange.
Orange. So if I took a light and shined it through Fanta, you'd be like, oh, there's something orange in that bottle. So I can see the colors of the stuff inside of the planet's atmosphere. And knowing the colors will tell me what it's made up of. Long story short, there's spectroscopy instruments on Webb. Not just taking pictures, but we're also analyzing on Webb's instruments what elements, what materials we're seeing on these planets.
And that's incredibly hard to do because the stars are bright, the planets are tiny, and the atmospheres are just minuscule. And so getting that contrast is really hard. But having this huge infrared telescope in space is going to, again, I think just sort of blow open the world of how we understand exoplanets.
Let me talk about like the craziness of sending this thing. Do you remember hearing about a space mission where astronauts had to go up to Hubble and fix it?
Yes.
We will not be able to do that with Webb. So everything has to be perfect.
Why?
I'm curious what you think. Why would we send Webb so far away?
To get away from Earth's light?
Ooh, well, that's one of the reasons, yeah.
Actually, it seems crazy to me because
You gotta get it right on the first time. You can't fix it, and it's $10 billion, yeah. So why would you put it so far away? That's crazy. So the reason why is that when a satellite is orbiting Earth, it often passes in and out of Earth's shadow. And so it's heating and cooling and heating and cooling. There's this really special point that they're sticking Webb, or it's actually already there. It arrived already. And the point is called a Lagrangian point. So there's really, really unique points. Okay, so there's these 5 special points around the sun and Earth orbit called Lagrangian points. These are the spots exactly where the sun and Earth, the gravitational pull, exactly match with the orbit of your object. Where do you think that Webb is going?
I'm gonna guess L4 or L5.
That's a really good guess because these 2 are actually the stable points.
They're essentially like a gravity pocket.
Yeah, it's kind of like a gravity pocket. But these ones are real, true pockets that you really get trapped in. Asteroids and random stuff get trapped there. Well, Jupiter actually has millions of Trojans. They're decent spots to send a satellite, but also you're running the risk of there being something there to run into. It's actually here. So
Oh,
it's
really?
kind of, yeah. It's
L2.
going to L2, which is an unstable orbit. It's gonna need to keep using some fuel because it'll want to fall out. But the reason we want it there is to shield the sunlight and shield the Earth light. Here's my Webb. So it's got the sun shield down the bottom, and then it's got this array of golden mirrors here. Imagine this is Webb. The size of these sun shields is about a tennis court. So this thing is huge.
So when the telescope was being built, I could literally walk across campus and see the mirrors, you know?
Oh, that's so cool.
For me, I mean, just the sheer size of this thing, it is so big. For the first time I went out to Northrop Grumman in California to see the sun shield being tested, and they literally had a ladder there, you know, and you could walk up the ladder and then look down at the sun shield. And I'm like, it's hard to believe that that thing is in space now, because it really is. It's so big.
We had to send it folded up. So we sent it in an Ariane 5 rocket. There's so many people whose lives went into this, and it launched successfly. And not only that, I loved watching the articles because then it was like, the next step is we have to unfold the sun shield. So that thing, this part, this like silver part had to be unfolded.
I mean, the fact that these deployments have happened just like almost completely flawlessly, so incredible.
31 minutes in, the solar array comes out, and then high gain and little bloop, bloop, little antenna. Yeah, the sun shield palette, and this is 4 days after the launch. It is literally a transformer, Levi. And there was all these news articles going on like, we've successfully deployed the space shield, because we can't really, there's no GoPros on there. Ooh, love it. Okay, I don't know if you saw, but that was like These sun shields are a membrane of plastic. Incredible tech. Let me tell you about it real quick. It's called Kapton. This is actually really similar to like the space blankets that they use to keep you warm. But what's so incredible about this is that these have to be tensioned and pulled out because they're really thin. Is like a 0.5 millimeter thick layer of Kapton all the way down to 0.025 millimeters thick on the innermost layer. On the hot side, it can withstand about 231 degrees Fahrenheit. And then on the last layer, it's gonna be about minus 394 degrees Fahrenheit. Super cold. You've heard of absolute zero? Absolute zero refers to 0 Kelvin on the Kelvin temperature scale. So this is about 36 Kelvin. So that's really freaking cold. So the last thing I want to tell you about is just all the amazing tech that's on this. What makes a telescope really good is how big its mirror is. This is Hubble's primary mirror, and this is James Webb Space Telescope. Yeah, it's huge. Since space is brutal, I'm gonna give you some brutal statistics. So each of the mirrors, there's 18 hexagonal mirrors, each of them weighs 20 kilograms, which is about the weight of 4 severed heads. No, like have you been beheaded with 3 of your friends? Put those together, it's one of these mirrors.
You know, this whole thing has been very confusing until you just put it in perspective. So the whole thing, it's gotta be a lot of severed heads.
Brutal. The mirror is coated with gold, which is pretty cool. If you take the mass of all of the gold coatings, it's about the size of a golf ball. Spread over 6.5 meters, you take that golf ball, so it's super, super, super thin. It's about as flat as you would be if you were launched from a trebuchet and splatted against the castle wall.
Oh, okay.
Brutal.
That did not get any more clear, but thank you.
But actually that's not even accurate. It's way flatter. It's about 1,000 times less thick than a coating of paint.
I was gonna say.
Blood. This is about 1,000 angstroms.
Why do they need a thin layer of gold?
This chart of reflectance of a couple different metals. And check this out. So here's wavelength. So you're going this direction, you're going like, this is kind of like ultraviolet to the visible part of the spectrum. And then as soon as you get past 500 nanometers, gold goes from like, I don't know, 40% reflectance all the way up to almost 100. So it's better than aluminum. It's better than, what the heck is Ag? Do you know what Ag is? Silver. Yeah, but look, it's even better than silver. It's even better than aluminum. Gold just jumps right up to nearly 100. So you're looking at like 99% reflectance. It's so funny though, as a physicist, I read this and I was like, I want to see what the reflectance chart looks like. And I looked it up and I was like, oh, look at that. Anyway, they ended up making the rest of the mirrors out of beryllium. It's just an incredible instrument. So what's next? Well, they've sent it into space. It's there. They're going to align the telescope, so they have to check that all the mirrors are there and everything. Like they have to align them and test them, and they're gonna do that. They're gonna calibrate it using a star called HD 84406, which is part of Ursa Major, you know, Bear constellation. They're gonna get a very good look. Then they're gonna start looking at these galaxies at the very beginning of the universe. They're gonna start looking through nebulas at planets. They're gonna start looking for forming stars and forming planets and forming galaxies. They're gonna start looking for how our universe came to be. A huge moment for science and for engineers and for NASA and for, you know, international collaborations. It's very exciting.
That's so cool.
What was so amazing about the Hubble Space Telescope was that it showed us just these incredibly beautiful images of exactly what we would see if we looked with our eyes. So, but Webb will have to translate the images. We can't see infrared with our eyes, so it's like hearing an alien language and having to translate that into human, but you're still hearing a freaking alien language, so it's super cool. Thanks for watching. I hope you enjoyed and stay safe out there. Oh, happy physicsing.